welcome friends once again to the NPTEL MOOC module on handling large scale data using Stata. And large scale we mean we are trying to handle the large scale unit level data which our students, our social science management students largely use unit level data for their research. So, so this course is accordingly meant, and in last two lectures particularly I tried to explain the linear regression issues, and on the very third lecture basically in the previous two lectures we discussed the prerequisites of the linear regression and where you must be very cautious enough. And today, as I promised in the last lecture, that we are going to have at least for half an hour to 45 minutes on the commands or the Stata operations of linear regressions, pre as well as post estimations of this particular analysis. So, let us start it, and so to begin the linear regression model, we are supposed to understand the very basic assumptions of the model. Some assumptions start with linearity. Now, that is the very most and beginning assumption of the linear regression model. Even almost all the models in econometrics, it assumes linearity. Okay, or after some approximation they linearize the model, and then interpretation gets easy. So, in this context there exists, we need to understand that it is the need of the model to have a linear relationship between dependent and independent variables. Now, the expected value of y is a linear function of the x variable, which we wanted to say. That means, if x I changes by an amount of an unit change of delta x, holding other variables fixed, then the expected value of y changes by a proportional amount, that will be with the coefficient called beta I delta xi for some constant beta I that could be negative or positive depending upon our relationship of the variables, and in the model whatever we are going to get it. So, the total effect of x on the expected value of y is the sum of their separate effects. Okay. So, then only the total effect can be calculated. The regression model is actually linear in terms of parameters, that is more important, and I mentioned several times. Okay. So, that is linear in parameter, but not in not necessarily for its variables. Okay. So, this is one of the very important assumption, you must be very careful and then try to understand the logic that we explained earlier. Now, there are a number of ways to check whether a linear relationship exists between two variables. In Stata, one such example is through scatter plot. Okay. So, we will try to establish this, and through understanding whether there exists linear relationship or not. We will clarify what we mean by linear relationship. So, the scatter plot gives us scatter chart, scatter graphs, scattergrams. These are also called graphs, scatter charts or grams, etc. The mathematical diagram to display values for two variables for a set of data. The data is displayed as a collection of points. Okay, different points will be plotted, and that is being displayed with the scatter plot. The plot dependent variable, it actually plots the dependent variable against the independent variable. So, this can visually inspect the scatter plot to check the linearity. So, positive trend means there exists positive relationship which is clarified as one set of values increases, the other set also increases. Okay. So, whereas the vice versa is valid. These are explained in figure A and B. A refers to increasing trend and B refers to negative trend, whereas in C there is no trend. So, accordingly we can define that A explains positive correlation and B negative, and there is no spurious correlation in case of C. Coming to other backdrop of understanding the linear regression and its applications. the residuals are assumed to be, we are now going by another assumption called independence of error. Okay. So, independence of error also referred to as autocorrelation. Let us clarify autocorrelation, that the residuals is function is mainly dealt. The error functions are assumed to be uncorrelated with each other, like error function of the period t or t minus 1 or should not be actually correlated, which implies that UI are also uncorrelated. The correlation happens because of some reasons, mainly two reasons we are referring. One is related to model misspecification or time sequence data, which I just said. If an important independent variable is either omitted or of an incorrect functional form, the residuals may not be independent. Okay, if by any chance there are incorrect functions are taken. So, it is suggested to use proper functional form or use of multiple regression. In case of time sequence data, if regression analysis is performed on data taken over time, the residuals may be correlated. Residuals over time actually correlated, because generally they go by a average time, and that average trend keeps on continuing over time. Okay, so there occurs correlation. These kind of correlation are termed as serial correlation also, when time series component are there, and it is common in time series data, as I just mentioned. Okay. Now, for instance, there exists positive and system. For instance, if the error for one observation is positive and that systematically increases the probability that the following error is positive, that is a positive correlation. If the subsequent error is more likely to have the opposite sign, that means it is negative correlation. The problem is broadly known as autocorrelation, which we have just clarified. Now, symbolically we present that covariance, basically correlation between two error term. The covariance between EI and epsilon I, or population error in case of population data, otherwise small ei and ej, given the x, given conditional upon the independent variable which from where the error term is generated, the covariance must be equal to 0. Okay. So, where I and j are actually not not the same. Okay. It should be a different series of data. So, the error term has a population mean 0, that given the third assumption is more important as well, as the average error, the average mean error should be actually 0. Okay. And there should not be autocorrelation. Okay. So, therefore, the covariance should be equal to 0. Then now we are saying the estimated value of the error term given x should be also 0, which is explained by here, expected value of EI is equal to 0. Now, as a result of these assumptions, so when the expected error term is 0, if you take in the standard regression equation where yi is equal to beta xi plus alpha I or beta xi plus ei. Now, given conditional upon x, if I take it and then I take the expected value, now this component boils down to be 0. So, that means the expected value of this is nothing but the beta of x. Okay. So, expected value of the dependent variable is nothing but the beta of x, and accordingly we can estimate the function. Okay. The beta value can be estimated. Now, all the regressors are uncorrelated with the error term. Okay, that is another one, another assumption as required for the linear regression to be followed. All the regressors, the explanatory variables should be also uncorrelated. So, it also the assumption is also called exogeneity. Okay. Now, if an independent variable is correlated with the error term, okay, so basically says that regressors are uncorrelated with the error term. Okay, and there are some difference to it as well, uncorrelated with each other as well. We are going to discuss that. Okay, and with error term, basically the correlation between the xi with the epsilon should is equal to 0. Okay. Now, if an independent variable is correlated with the error term, regressors can be used to predict the error term. okay, which violates the notion that the error term represents unpredictable random errors. Okay. So, therefore, it misleads the prediction. Some of the possible reasons for this violation are simultaneity between the regressand and regressors. So, omitted bias, omitted variable, some variable bias or measurement error in the regressors that result in error term and the explanatory variables and their relationship. Okay. So, the assumption of exogeneity is also important. Now, coming to the issues of variance of the distribution error term, we are now going to emphasize another assumption called homoscedasticity. The meaning of homoscedasticity derived from the Greek word with homo refers to equal and skedasticity refers to variance or scatter. The variance of each error term, that is epsilon I, given the value of x, is constant. Okay. So, that means there must be it is expected that the homogeneity the homoscedasticity ensures that the variance of the error term should be actually constant, it should not be varying every time. If it is varying, then it is difficult to predict. If the variance changes, it is referred to as, if that is not sigma I sigma, rather if it is equal to sigma I square, then this is called heteroscedasticity. Okay. So, every error term correspond to and its variance correspond to a different standard deviation or variance is led to the problems of heteroscedasticity. And so, therefore, a different scatter information can be derived. To check this assumption, we create residual versus fitted value plot. If the spread of that residual increases in one direction and appears in cone shape, can be concluded as presence of having heteroscedasticity. So, either it is rising in a cone shape, or that means is constantly changing, or changing in certain direction, that is called heteroscedasticity. Okay, problems of heteroscedasticity. So, usually cross sectional data or studies often have very either very small or large values. So, that amounts to heteroscedasticity. So, it has higher likelihood of having heteroscedasticity, because either some responses are having very small value or having very large values, the deviance between them is actually very high. So, heteroscedasticity is very likely. Now, the sixth most important assumption is multicollinearity. There should be no multicollinearity is the assumption. So, in the previous one we said there should be homoscedasticity, no heteroscedasticity. Now, in case of multicollinearity, we wanted to say that there are no perfect linear relationship among the variables or independent variables. Okay. So, perfect correlation suggests that two variables are different forms of the same variable. Okay. For example, games won or games lost have a perfect negative correlation with -1, is not it? The temperature similarly in terms of Fahrenheit or Celsius have a perfect positive correlation, that is +1. If these correlations are high enough, then they can reduce the precision of the estimates of the OLS regression OLS linear regression estimations. Now, coming to the seven most important assumption is normality of the error term. We are going to explain you what is multicollinearity in the data, what is heteroscedasticity in the data. We are going to explain with the help of experiment with the real example or the data. So, next assumption is normality of the error term. The error term must follow a normal distribution. Okay. So, having normal distribution having 0 mean and constant variance. We have already assumed that variance must be constant. So, now and also we have assumed that the estimated value of the error term should be equal to 0. So, that way again it validates when both are followed. So, that means we will be eventually following a standard normal error distribution, and that is explained with the help of this epsilon I distribution follows normality with 0 mean and variance sigma square. Okay. So, now let us illustrate of the linear regression in unit level data. Using the unit level data, we are going to explain how we follow our the important assumptions. Okay. So, for this purpose actually we are using 7/3 data of National Sample Survey that is that was conducted in 2015-16. So, we are going to use a data and a sample data before us that is with the name we are going to provide it for your practice that is with the name regression underscore practice data. So, we are interested in examining the factors affecting the performance of female owned enterprises. Okay. The performance of the enterprise is proxied by here we are going to understand the performance of the female enterprises and that will be proxied by the gross value added that information is given in the data. So, the some farm level variables are taken as explanatory variables and those will be used. Okay. Please take a note that the purpose of this lecture is somehow is to somehow somehow use different commands for regression analysis. It does not give the exact model used for research purposes and the required testing after regression. Some important aspect we are going to discuss that does not mean it gives the exact model. There are lots of experiment made in between for getting the right model and right result. So, here is the details of our variable of dependent and independent. In the dependent we said that we are going to use gross value added per capita terms and its log value we are going to use it to normalize the dependent variable. Okay. I will tell you whether it is normalized or not through log transformation. Okay. And and independent variable we are going to use sector that is rural and urban, social groups in terms of caste, then location of the enterprise, then enterprise type, own account enterprise or establishment. Similarly, we are also using computer use, loan outstanding, age of the enterprise. So, basically 2016 minus initial years of operation, if you do it we get those information for our explanation. Okay. So, now what are the steps we involved for running the regression? First of all, we need to examine certain descriptives of the variables used in the model. So, and we will understand the relationship graphically also and also test their correlation and then we will run and interpret regression. So, then at the last we will test those assumptions whether those assumptions we have taken whether those have been proved or rejected are going to be understood from the session. Okay. So, now it is always now we are going to examine the descriptive statistics as I just said. It is always advisable first to examine the variables in the model to check for possible errors. Okay. So, so we will begin by using the describe command which we used earlier to list various features of the variables to be used in the linear regression. So, now type we need to type the in the command window as describe of those variables dependent as well as independent and that is going to give us the right result. I think if you have forgotten we are going to operate right now. For simple linear regression model we are considering only 2 variables. Okay. Otherwise, you will be using the multiple regression with multiple independent variables. So, now I am going to switch the mode to the the regression mode regression commands. So, here is the window of the data and we are going to use the data which I said already. So, our data is here and so we are going to use the practice data. Okay. So, now this has already been opened. So, what we do we will go by the variables which we have already shown to you. So, the log of the GVA we have already converted I think. So, and I think it is at the bottom. Okay. So, now this is there and any sample variable you can use for our clarification or simply describe everything together you will also get except some other variables we are not interested for our explanation we should not do it. Okay. For simplicity I am simply copying the variable, otherwise I'll if I type describe only D. Okay. So, okay, all right, DES, then if you just click here this and any independent variable, this will give us some description. Okay. Like loan outstanding, like nature of operation, location, etc. If I simply enter it, it gives me the description of those variables. Okay. Now, this also emphasizes whether the variable is in string format or in numeric format, that those aspects we have already clarified earlier. If you have some difficulties, please follow our previous lectures for better clarification. It also gives variable labeling. Okay. So, variable labeling are also emphasized or also derived. Now, without wasting much time, these are very simple and I am quite sure you can able to do it. Okay. So, let me proceed. Now, if I do describe these two, okay, one dependent variable and one in the total worker. Now, I will get this type of picture which I have just shown you. Okay. Now, the describe command gives information about variable storage type, display format and value label and variable label. The variable types and format columns indicate that all the data are numeric, okay, that we have already shown to you. Okay. So, you cannot actually run regression if the variable shows with string variable, you need to destring them and then you can go for the operation. Okay. Now, so it is essential for in any data analysis to first check the data by summarize command. Okay. So, not just the describe is not going to give all the information. Likewise, what I did just now, if I just explain you with the same variable, okay, just I wanted to find out that I will use instead of describe I will use summarize. Okay. So, I will get certain information for sure and which are going to be useful for further. Okay. Now, in the summarize command we will be getting the observation details, the average value of it, the standard deviation, the minimum and maximum values of each of the variables which are useful for us. And usually and these figures are expected everywhere in all your paper for publications. Okay. Wherever you communicate, they will certainly expect you to give the summarized table. Okay. So, I am not going to derive the same result, you can experiment and find out. So, the observation column tells us that there is no missing values, because the number of values which are there in the data in this result also we do not have any missing value. Okay. And how to deal with those aspects we have already mentioned earlier. Okay. Similarly, if I just go by all the variables together, okay, so I will get all such information and it clearly emphasizes that there is no missing value and all the observations are visible before us. Okay. Now, another useful command for variable description is also tab. If I simply tab it, tab that particular variable, it gives me the frequency distribution of that particular variable. Okay. So, let me proceed. Now, we need to understand the correlation and graphical representation of the variables in order to understand some of the details very clearly. Now, to check the relationship between variables, scatter plot helps in understanding understand this graphically. These two variables of interest of us in case of bivariate model. So, simply scatter plot, and if I click these two variables, then I will probably get it, and sometimes scatter plot may not it might require installation. So, let us test. Okay. So, like here, okay. So, the two variables of our interest is here and number of workers, total workers, I think this. So, if I just do it, now as I told you already, it is saying on recognize command, then in that case what you need to do, you have to search. Sahaj-Cuttle plot, and accordingly you can derive it the way we guided earlier. Now, what I will do instead of that, I will quickly go to understand another approach of understanding the relationship through graphical presentation of to a table. Okay. I will simply do one thing. To save our time. So, what I will do, I will go to this, and we will come to the the particular slide, and yes, this is the one, and let us copy that. You can test on your own. Okay. So, we will copy it and we will paste in the respective starter window. Now, once I paste it and then I will go for entering the command, it will certainly give us the right direction, and the result is there to come. I think it is calculating, estimating. Yes, we have got the graph. Now, after getting this, we can we get many information out of it. Now, look at the average number of walkers. So, what we actually what we really submitted to the starter window, that what is the two-way table, two-way graph between per capita log per capita GPA and total walkers with a title that average walker 2 per capita GPA. So, the title, if you mention it, it comes at the above, average walker to per capita GPA. Now, the per capita GPA in the vertical axis and average number of walkers is there on the horizontal axis. Now, a point is completely a point is coming and highlighted here, that which represents 200 walkers are walkers having the log per capita income represents 200 walkers. Okay. Now, among the average walkers, this is one outlier. You can easily understand this is a clear outlier, and the outlier suggests that from the diagram, if I can interpret like this, it is like only one that is one enterprise having 200 workers. Okay. One enterprise has more than 200 workers. Okay. It is more than 200 workers, and and plotted against the log per capita GPA. Okay. And this plot also suggests that higher the number of average worker, higher the GPA. Okay. That is roughly highlighting the positive relationship, but how to understand it unless we do not have a trend line. Okay. So, but somewhere higher amount of GPA, per capita GPA is associated with the increasing trends of average number of workers, except in one case. Okay. So, for that we will take the help of to fit the line, whether it is actually rising or not, we have to take the help of a fitted line. Okay. So, let us copy this, then we will operate this, and then in the startup page, if you operate, we will find out the result. Okay. Now, from this it gives me a fitted actually fitted line, not just the graph, it also gives a upward trend line. Okay. So, this red line highlights fitted values. Okay. Now, this shows that there exists a positive relationship. Alright. So, we are not spending much time on it, and what it indicates is more important for our explanation. Alright. And this is what we have explained. Now, the fitted line shows the positive relationship as I just mentioned. Now, we will check for the correlation between the variables of our interest. Okay. Now, correlation can be checked with their significance level as well. Now, simple correlation, if I type this dependent and independent variable, we can get that. But just correlation may not have any interpretation unless we have any forms of its significance level. Okay. So, we will attach the significance level to it as well. Alright. So, let us go by that and experiment this from the data. So, this is the one PW. Yes, all the variables are selected and we are operating through the regression window. Okay. Now, with the okay, once I enter it, we derive the results. All the correlation value, its 5% significance level has also been interpreted. Now, you need to understand very clearly that the significance level here we are mentioning as 5%, you can change it to your number at other indicative level as well. Now, so which variables are positively linked, which are negatively linked, are clearly highlighted. Okay. So, there are two window here all the variables and its correlation is highlighted. Okay. From the correlation we can establish whether the variables are actually linked to each other or not. So, this is what we said. Now, now the plus and minus sign regarding their relationship has already been mentioned. Somewhere we get positive, somewhere we get negative. So, higher values of rho represent stronger relationship. The correlation, if it is having higher value close to 1, generally that indicates better correlation. Okay. Otherwise, there is a weak correlation. But the significance level actually identifies even if there exists weak correlation, but those variables are important for analysis. Okay, if significance level gives you the direction. Now, coming to the explanation of normality of the y variable, the dependent variable, okay, and that we can identify through this data, and one of the approaches of measuring the normality is to histogram. So, histogram and the variable name, if I just enter, we will actually get that. Okay. So, simply histogram and the variable name. Okay. And this is the one, and if you enter it derives the histogram with different beans. Okay. Now, different beans might be difficult to read at a go and might be problematic. We need to restrict it to its to its indicative level. Let it be we are going to control with a 20 number of beans. Okay. So, now but if you want to plot the normality of that particular histogram, you need to add with a comma normal bean 20. Okay. If I just simply do that, then with the same command then normal, okay, double, okay, normal, then bean 20. All right. Now, you will get the normal plot of that particular variable, that is the dependent variable we are supposed to take is the log per capita GVA. Okay. It seems that the dependent variable is approximating to a normal distribution, and one of the approaches has made it near normality because of the log transformation of the GVA. The original GVA is generally not having normally distributed. Okay. So, now let us move on to understand some other details. Okay. So, I have to close this, then only it will work. All right. So, here we are, and we are trying to explain the normality diagram that we have done it. Now, I am going to discuss about the another approach of understanding the details of okay. So, now the kernel density plot, this is an alternative to histograms, and which approximate the probability density of the variable. The kernel density plots have the advantage of being smooth and of being independent of the choice of origin, unlike the histogram. Okay. So, we can experiment and I can find out. Okay. Now, so here is the okay. So, with the same command, only k density, we are writing k density, the same y dependent variable, then normal. Okay. So, that gives us a smooth smooth diagram, the kernel density estimate is presented against a standard normal distribution. So, it is almost approximating to the distribution. Okay. So, so now this is what we have shown. Now, I wanted to mention that there is a command we need to note that we have already checked for normality of the y variable. So, initially we converted the original variable, that is GBA, into a per capita GBA, then we took the natural log of it. Okay. And we can check for different transformation of which the y variable is normally distributed through a GLADR command. Okay. GLADR command actually establishes whether which particular transformation is most fitted, okay, most appropriate for converting to a normality. Okay. So, let us go by the GLADR and the per capita GPA first, okay, then we can generate in terms of. Okay. So, it looks like this. If you go for it, the same command, you will find this type of results. Okay. So, out of all those things, so many different results popped up, and now it seems that the log transformation of this of this particular per capita GBA is approximating to a normal distribution. Okay. So, I think in not spend much time, we have many information to be explored. Now, let us come to the model estimation. So, regarding y variable and its normality, we have already explained. Now, let us understand the model estimation. Beginning with simple linear regression, in which we only have one predictor variable. In Stata, the dependent variable is listed immediately after the regress command. It is followed by one or more predictor variables. So, simply we will write down regress, okay, its dependent and independent variable. Now, one of the very good important suggestions to you that you please try to run another regression command to it after regress, so that we can compare all the models to EST-STO command. Okay. Of that model 1, similarly in the model 2, I am going to show you in model 2. So, let us see if it is not there, we can install it and accordingly we will move further. Okay. So, let us explain these two together first. Okay. So, in that case it will be of EST STO. So, the first suggestions we need to install. Okay. So, after installing only it will work, and it gives the right window for comparing the models. Okay. So, it is being installed, and then only we can able to offer it. Now, the regression command takes the variables. Now, I think it has been installed. Now, we are going to start with REG. So, it will be REG, so then dependent variable and independent variable. So, this is the dependent variable we wanted to discuss, then number of workers. Okay. By entering it, we derive the results. Okay. Now, followed by that, you have to go by EST STO, then we will let us write down as model 1. Okay. Now, this has already saved, basically EST STO actually saved the results of the model 1, and then at the end we can able to compare. Now, what are this is the regression result with one independent variable. Similarly, you can go for many independent variables if I mention, and the results will display correctly. Okay. So, here is the result, and what is important to be mentioned, everything is given here, that we start with the command is here as outcome variable is here, then the predicted variable is here highlighted very clearly. Now, this result is also gives the significance level, the F test value, and it suggests that the R square value is around 4%, then adjusted R square its value is also given, we have already clarified in the previous lectures. that it says that around 4% of the variance in per capita GPA is explained by the average number of workers. Okay. Now, the root mean square error, it gives that it is the it is the standard deviation of the regression. Okay. The closer it is to 0, closer is to 0, it is the better fit for the model. Okay. So, less mean square basically less standard deviation. So, better is the outcome and better is the model. All right. Now, last one in this particular result to interpret is that the intercept term, that is constant term, should be treated more carefully as it is in log form. Okay. Because our dependent variable is in logarithm transformation. So, to get that for the interpretation we have to take antilog of that coefficient. Okay. If you do not take antilog, I think the right interpretation is not there. Therefore, the fitted line is written at the top as this. Okay. So, the fitted line suggests that you have to take the antilog for the interpretation. The coefficient is of interest is that the coefficient we have derived this 8.01 is mentioned here, and the total worker at the beta coefficient is given here. Okay. So, if you just fit those things, we can estimate and estimate the equation correctly. Okay. So, and also we have entered the ES2 S2 command, and at the end we will operate with EST tab to find out the result for comparison. So, let us understand another approach for another model also. Okay. So, regress, then we will copy this and or we will operate these variables, and I wanted to show that how ES2 command works. Okay. So, it is here. So, then all right. So, let us go to that window. Okay. Simply we will copy it and operate this through our stata, and the stata gives the result. Okay. Then you can save with ES2 STU model 2. Okay. Then this is already saved. Now, I am not interpreting much on this, it is more or less similar. So, we are going to discuss another okay. Now, okay. Another aspect, now it is more important. If there are so many variables, there are some dummies variable, dummies in the regression command. Okay. To emphasize the dummies, just averaging regression usually does one thing, it simply averages the variables. Okay. So, what so far in both the models we have taken the averages, but now if you bifurcate by the dummies, we can include a prefix command with with I. Okay. So, by default the first category is considered as a reference term. We are going to show it right now. Okay. And for that we need to operate with a xi command. Okay. So, okay. So, let us go by that command now to operate. Okay. So, xi command is there, xi then regress, regress, and wherever we have dummy variable we have taken I dot. You mark this carefully, and the I dot command is going to give us the correct result. Now, we have got the result, and the dummy variables now also will save with ES2 model 3. Okay. Now, I just wanted to mention that you have already seen these basic results like F test, its significance level, its R square, adjusted R square. Okay. I just wanted to say, when our sector is a dummy, it has by default considered 1 as the first reference category, as compared to 1 sector 1, that is rural area. Rural has been considered as the reference category or the base category. Now, as compared to rural, the urban coefficient is 0.22, okay, 0.221743, and that is significant in our model. Okay. Similarly, other social category, then 1 is considered to be the base category, then 2, 3, 4 are considered the other categories. Okay. So, interpretation is made accordingly. So, now at the end, after discussing all those 3 regression models, we are there to compare. We are now going to understand the EST2 command and its results. Okay. So, we will just take this there EST command. okay, then we will paste it and then we can also find out the result. Now, look at all the models so far we have taken is presented here. Okay. Its model 1 is presented here, model 2, model 3, and in model 1 if you remember we have taken only one variable, then in model 2 there are 3 independent variables, okay, and in model 3 all other variables have been taken. Okay. Now, important very important for the paper, in most of the papers they do require comparison. Okay. Now, you can find out that the R square are also compared, the adjusted R square is also compared. Now, look at in the third model adjusted R square or the R square value is more than 31% as compared to other two. Okay. So, therefore, we may consider that the third model is more fitted. Okay. 4 fitted, and that too the root mean square error is also less than that of the other two. Okay. So, other two. So, the third model, since we have considered more variables, more diversity is there, that explains the model correctly. Okay. And accordingly that also reduces the R square value. Okay. So, no that reduces the mean root mean square error, that is the variance term has been reduced, but the R square value is actually increasing. Alright. So, let us move for some other clarifications. We have almost dealt with most of the important aspect, but some other interpretations are still left. Okay. Now, to control for heteroscedasticity, okay. To control for heteroscedasticity in the model, we can also include, I think we have already discussed the aspect of heteroscedasticity, we can also include robust options. Okay. So, robust options actually gives us the unbiased standard errors of OLS coefficients and that is discussed under heteroscedasticity. So, to get the standardized coefficient include beta options in the end of the command, and standardized beta coefficients are reported instead of confidence interval. The beta coefficients are the regression coefficients obtained by first standardizing all variables to have a mean of 0 and a standard deviation of 1. Okay, that we have already discussed earlier. Beta coefficient can be useful when comparing the effects of variables measured on different scales or in different units such as inches or pounds. Okay. So, there are some points for consideration to understand the fitting or estimating a model. There are two majorly we are discussing at this moment. First is the fitting the maximal model. The maximal model is the large model that contains all the explanatory variables of interest. This model also contains all the covariates that might be of interest. Okay. This contains the interactions that might be of interest. Note that the amount of variation is also explained. Okay. So, begin simplifying the model through inspect each of the terms in the maximal model with the goal of removing the predictor that is the least significant and drop from the model of the predictor that are least significant. Some of the variables will drop to find out the best fit. So, fit the reduced model, compare the amount of variation explained by the reduced model with the amount of variation explained by the maximal model. We are going to discuss in our slide. So, the strategy to keep or drop variable is important. So, the predictor not significant and has the expected sign, okay, then we need to keep it. Okay. So, keep the command we already mentioned, the predictor which has better expected sign, we need to keep it. So, keep and that variable will actually keep. If you write down keep and variable name, we just write the variable name, it will keep the variable name and it will drop other variable names. Okay. If you when you are doubly sure that this is not important and does not have the expected sign, then drop that variable. Alright. So, predictor is significant and has the expected sign, then keep it, we have already said, and then predictor is significant but does not have the expected sign, then review it. Okay. You may need more variables in order to have better result and can the it may be interacting with another variable in the model or there may be an error in the data. How good is the model will depend on how well it predicts the y. The linearity of the model and the behavior of the residuals is important. Generating predicted values of the variable of interest after running the regression is very important. Okay. So, generally we go for predict, predict, then the variable name. I mean, if you do it once our regression, since our regression has already been, once again we will run the regression, let it be this is the regression. Okay. So, simply if you enter it, then we get the regression result, then followed by predict, simply predict, then okay. Predict, and if you take a name of that variable, since we are predicting the one, better to write down with a hat, is not it, with a name underscore hat, and that gives a predicted variable, is not it. So, I think this is the one, a hat has already come here with the name hat. Okay. All right. So, so generating values of the residual, how to do it with the same approach, the way we have done it is simply predict R comma resid, it gives the residual details. Okay. So, now checking the model assumption and fit. So, like the model checks require you have I mean checks require you have just feed the model you are checking, save the predicted values of y and as y hat we have just mentioned. So, then plot, observe and predicted values of y variable. Okay. So, if you do it, then it will find out, it will give, if you then copying that and operate it, or if you know the right word to be okay. Now, this is not the one. Okay. Now, if you after predicting, now we can get the fitted values and the predicted values of our model. Okay, that has already been explained to you. So, what I will do, I will now explain. All right. So, that we can predict, and this will look like this, and ideally points will fall on the x and y line. More falling more points are assembled nearby that point or on that line. Okay, that model is expected to be better fit. Similarly, we can check the normality in residuals. So, 3 graphs will help us check the normality, the k density, okay, k density, and then or p normal probability normal distribution or quantile normal distribution actually gives the normality of the distribution. Now, from there k density r normal, if I just do it, then probably we can able to do it. Okay. I think we need to have regression first, predicted values of the residual term. Okay. Then we can find out the k density of and the normality of that diagram. Okay. This is what we wanted to show here. All right. So, now where is that? Here is the one. Okay. So, this is the diagram we wanted to refer. Okay. Now, it is approximately overlapping with the standard normal distribution. So, we can assume that our distribution is better having a normal density function. Okay. So, what is important here to note that the standardized normal probability plot, that is P norm, checks for non-normality or in the middle range of the residuals. So, for that you simply go by the command P norm R, and if you go by a title like this, we can explain it correctly. Okay. 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 So, it gives us the plot, and it is almost overlapping with the standard the trend line. Okay. So, that will be very useful for interpretation as well. If it is completely deviating from it, then it might be problematic. Okay. So, slightly off the line, so but looks perfectly fine. Okay. Now, similarly quantile normal plots can also be derived. Okay, with Q norm R, then if you title and you go and check on your own, and you will certainly find out. It plots a quantile of residuals versus quantiles of a normal distribution. Tails are a bit of the normal, so but still it is largely overlapping. So, the distribution looks better. Okay. Now, another couple of things are there to find out. Okay. So, let me just stick to the last important guidance for you, that after having the result, regression result, we need to understand whether there exists multi-quantity or not, whether there exists relationship between the variables or not, whether there exists perfect linearity between the independent variables or not. Okay. For that we need to check the VIF function. Okay. So, VIF is going to give us. So, so VIF, if it is less than 10, then no, it is perfectly fine. Okay. So, if it exceeds 10, then that is problematic. All right. All right. So, if VIF is exceeding 10, or the inverse VIF, that is variance inflation factor, if it is it is less than 0.10, inverse, that is 1 upon VIF, that is inverse of it. If it is less than 0.10, it indicates a trouble, that means there exists multi-quantity, and we need to check accordingly. So, the finally, the last one to be guided in this session is testing of homoscedasticity. Okay, the Bros-Pagan test detects heteroscedasticity in the model. The heteroscedasticity, we told you that the variance is having sigma I square, or the variance of the error term varies. Okay, but our assumption is that there should be homoscedasticity. Okay. So, the E start head test is going to give us, this is like the okay, okay. So, E start head test. All right. So, it has given us the interpretation for interpretation. Now, our assumption is that our the null hypothesis is that there should be constant variance or homoscedasticity. But now, we have derived that our result is significant. That means, we are actually rejecting the null hypothesis. That means, our data has heteroscedasticity. All right, and if there occurs heteroscedasticity, the model requires further check. Okay. In our model, there is a presence of heteroscedasticity, so we reject the null hypothesis of the homoscedasticity, although we have suggested in previous slides to use robust options to control the heteroscedasticity. Okay. So, that is all the guidance so far. In this week, we have covered everything about linear regression model. Okay. We discussed so many things. I think if you go carefully and operate on your own from the slide with the sample data, you will enjoy in reading the slides. Okay. Thank you so much.